And this is illustrated with this nice AI-generated chart, where you see the end user driving the whole process, and we will have these acceleration pipelines bringing the technology from low TRL to higher TRL and up to market. And then we will continue doing our activity from developing the skills of the robot, so training and investing in that, but also in the qualification of this robot. So we need to understand the capability of the robot. So this is what we call the Robot Skills Qualification Center, which are supposed to become an independent body, which will validate the technology to also reinforce the trust in the technology. Because once you have qualified those robots, then the end user can trust that, okay, if you define a benchmark which says something to them, then they will say, yes, this is something I need, and I will therefore create, we want to create a market pool, and creating a market in Europe in identifying those important common needs that we need to develop and join forces to develop, because we have the capacity, but usually they are, scattered throughout Europe. We need to join forces and accelerate that process, building on all or the excellence that exists in Europe. So that's a bit the sketch of the activity. And I also want to announce two big projects that are going to start in June, and for an investment total of 85 million euro. So one project is 40 million, the other one 45. And the goal is to create an effort to build foundation model for robotics, for manufacturing, and another one, it's more foundation models for manufacturing, so not necessarily robotics, but AI model for robotics. We think it's important that in Europe we also have the capacity to master this technology, and we need an effort at scale to do that. And this project will also have the capacity to involve additional users later on with this process, which is called financial support to third parties. So they have called to address some specific part of the project, then they can, other partner can join later on. So that's just an input from my side, but we want to build on the achievement of our project to prepare also for the next generation of the robots. And today, we want to really see the winner of this selection of those success stories, and I'm really looking forward to hear from your successes. So we will have Canopies, then Darko, and then DG Forest, and then Somero. So you will see a variety of use cases as well. It's important to show what this technology can do to help. So thank you, and we then hand over to Andrea and Sarah to present the Canopy project. And I have a good news, because I think the camera is on and the session is recorded. So I saw this camera is very good. Okay. I remember when we launched your project, so now I'd like to see if the promises are realized.
Perfect. So, thanks, Cecile. I'm Andrea Gaspari from Roma 3 University. And today I would like to describe the result that we obtained within our project Canopies. The title was a collaborative paradigm for human workers and multi-robot teams in precision agricultural settings. Just a few words about the consortium. We had 10 different partners coming from 5 different countries. We had 5 universities, Roma 3 University from Italy, then we have KDH from Sweden, Sapienza, Università di Roma from Italy, then we have the Università Politecnica di Catalunya from Spain, then we have Università degli Studi di Cassino e Lazio Meridionale from Italy, and then we had one research center, the Danish Technological Institute, and 4 small and medium enterprises. There was PAL Robotics, who was the technology provider. It was PAL Blue from Norway. They provided us with a simulation environment. Then there was our end user, Agrivecina, and RSA that helped with the management of the project. The overall project was roughly 7 million. We started on January 2021, and we completed the project on December 2024, so 4 years. And I had the honor to be the coordinator of this team. So, just a little bit of context. The ambition of the project was to develop a novel collaborative paradigm between human workers and multi-robot teams for agricultural settings. We went in the direction that Cecile was talking. We don't want to replace the humans, but rather we want to help them out whenever there is a need. Actually, just a little word that I thought about saying while I was coming up, that the reason of this project was motivated by the fact that a company came to us telling us that one of the main issues in agriculture is that the activities are seasonal. So they do not have enough people for those peaks of activities. And then we said, why don't we try this paradigm in which we have humans that might have several roles, from collaborating to monitoring the activities of teams of robots. In this way, we can scale up. And then we came up with this vision in which we have farm workers that, as you can see from this picture, they will interact with two different kinds of robotic platforms. We divided them in what we call farming robots. That are the robots that take care of the agricultural task, for instance, harvesting the grapes. And then we have also logistic robots that take care of the logistical side. For instance, if you are harvesting grapes and putting them in a box, sooner or later this box will be filled in. And rather than moving around this robot that have manipulation capabilities, you want other robots that move close, replace the box that's being filled in with an empty one to let the first one to keep working. So how did we approach this problem? We wanted to develop efficient data-driven technological solution that would be at the intersection between AI and robotics in order to develop a more sustainable agricultural model for tomorrow. And we did that working across several different kinds of methodologies, ranging from human-robot interaction, human-robot collaboration, and multi-robot coordination. Throughout human-robot interaction, we were able to develop some methodology that allows to have an enhanced safety coexistence in this shared workspace. Throughout human-robot collaboration, we were able to be more effective in the cooperation throughout also an explicit interaction, as you will see, through natural language. And once you have a platform that does this work, you have to realize that in agriculture, fields are large, and you need to scale up. And so having an effective multi-robot coordination is crucial in order to be able to scale up properly. Now I just want to share with you some of the results that we obtained. Those videos are taken from the final demo, and I selected some of them among all the activities that we have achieved, the tasks that we have completed. In this case, we are talking about quality mapping. So basically, we have robots that move around in the vineyard. Clearly, those robots can move around because we also have developed localization and mapping algorithms that are reliable for vineyards where you don't have GPS access most of the time. In this case, you have the end user can select an area and can send a robot. The robot will autonomously move there and figure out what is the quality of the bunches that are detected. The quality is across 4 different directions. You look at whether there are anomalies, the bricks level, the color level, the size of the grape, because, I mean, table grapes are products that are supposed to be fresh, and there is a sort of standardization, if you will, of the quality that you want to see when you go to the market to buy them. And we need to check that everything is in place properly. Now, another example that we have developed is about human-robot interaction throughout natural language. As you will see in this example, we have a human, an operator that is talking to the robot, asking a set of information. For instance, he might be asking to harvest a certain bunch, but not only, you might even
the quality of the grapes.
You may even inquire the robot about the quality of the grapes that you see. The robot can move there, can tell, okay, the grape is ready, or is not ready to be harvested, and so far so on.
How many bunches can you see?
You can interact with them, all right? And just to give an example, it will ask a couple of questions. It will ask whether these are ready to be harvested,
Can you tell the color value
things like
of
that.
the grape bunch number 16?
We defined also levels of colors that define whether the grape is ready or not to be brought to the market, and things like that. Now, since the table grapes are
is a grape bunch 16 ready to be
complex
harvested?
setting, I think I might just want to take away the audio. No, I can't. All right. So basically what can happen is that sometimes, since the context is complicated, you might not be able to have the robot completing the task himself, and he can ask also for the human support. Here there is an example. I don't know if there is enough time, but basically the robot gets stuck because of the wire that makes the structure of the vineyard. And in this case, ask for the help of the human. The human could be, as we said, a supervisor that stays there with a team of robots. And in those particular situations in which the robot cannot complete its task, it can go there, help the human, the human can help the robot, and the robot can learn from his mistake and do better next time. Another example of activity that we have developed regarding the coordination is the operation of the box exchange, what we call the docking operation. Basically what happens is at a certain point, as I said, while harvesting, you will have that your box has been filled in, and then the farming robot will ask for the help of the logistic robot that has to go there, navigate, do the docking operation, exchange the box, and replace the filled one with a new one. And clearly, this has to be done autonomously, while in the same area, you may have also humans that are moving around. Also in this case, it might happen, a failure due, for instance, for the fact that the ground is uneven, things like that, and there is a way to try again, and if you keep failing, then you can call also in this case for the human help, because our idea is that we don't want to have a 100% replacement of human capabilities, because the setting is extremely complicated and dynamical, and the best solution is to have a paradigm in which they can collaborate together. So, last one, in terms of results, we wanted to share also this part concerning the virtual reality environment. We have basically developed a digital twin of the environment in which we were supposed to do the final validation in the field, and this has been extremely important for us, because going to the field is not the easiest operation, it's the most convenient, and being able to do prototyping of the approaches in an environment that's sufficiently equal to the real one to develop the algorithm has been crucial. Not only for that, I also believe that once we will get to the market with a kind of product like this, it's a really, really great tool also for the workforce training, in such a way that the farm workers, before to have to work with a robot that might be also expensive, it's good that they get practice throughout a simulator. Now I will leave the floor to my friend and collaborator, Sarah Terreri, who will talk about the exploitation part of the project. Sarah, the floor is yours.
Thank you. Good afternoon, everybody. Okay. Yes, as Andrea mentioned, we are one of the two companies included in the consortium. This is why, besides talking about the role that we had in the project, the results that we achieved, I also wanted to highlight the benefits and the impact that we got thanks to the participation to this project. Because it gave us the possibility, the opportunity to create the technological foundation for the development of our new generation of collaborative manipulators. Thanks to this project, actually, we have developed, going a little bit step by step, but very quickly, the starting point was our Tiago famous manipulator in its configuration, bimanual configuration. So for providing this task of harvesting and pruning, we have developed the prototypes for specific end effectors with the requirements that Andrea mentioned during the technical presentation. But besides that, we have developed our own, a new generation of arms. So we have designed and manufactured our own series elastic actuators, a new configuration of the arms with brakes in every joint. It's torque controlled. So it's safer, more compliant, and more collaborative compared to same let's say models present in the market. So it's collaborative manipulation while navigation in the environment. So the final results. So obviously the demonstration was in the field of agri-food, but this is suitable for application in many other sectors. So the final results was the Tiago Pro, which is the latest generation of manipulators. It has been developed under three main pillars, which are the advanced navigation, precise manipulation, and intelligence perception. It enables also seamless human-robot interaction, making it a collaborator in very different environments. So we had the chance to test it in collaboration in human in other applications in the agri-food sector, but we had also many other applications, also thanks to the European project in healthcare, logistics, retail, manufacturing, among others. Okay, so I will leave the floor back to Andrea for the conclusions.
There are not much to say. Thanks to everybody. I want to thank the consortium. They were a big and nice family, and I love to work with them. And that's it. Thank you. way.
Achim is
Just a sec. So, thank you. So, okay, let me start. So here we have Darko, and since I'm presenting in the session Success Stories from a EU-funded project, I think I can call it a European success story. That's how it feels anyway. So I'm Achim Lilienthal. I'm at Technical University of Munich, and I had the honor and pleasure to coordinate this project. It wasn't organizationally very easy, so we had lots of changes, and that's why I have, for example, 4 different scientific managers, which I list here, and they worked closest to me. And then I have the PIs of the different partners. So, for example, Martin Magnusson took over from me after I left Sweden in Örebro. There was Sami Haddadin for TU Munich, who was the initial PI, Tommaso Colombo from Spindox Labs, Nicola Bellotto and Mark Hanheide from the University of Lincoln, Aude Billard from EPFL, Paulo Salares from the University of Pisa, and Kai Aras and Arunas Vaskevicius from Bosch. So here you have all the partners. And then, of course, there were many more people in the project. I think in the end we had over 60 people without the master students who contributed. And I think it's very important to become a success story that the partners put in additional resources, which they did in this case. And then in the end, the project was running from January 2021 to the end of June 2025. So because we were hit by Corona, we got an additional half a year. So about Darko, how to explain it in 10 minutes? I think most importantly, the acronym actually means we are looking at intralogistics scenario, dynamic agile production robots. That's the first 3 letters, DAR. And here we specifically look at the single robot, so a robot that transports stuff and that actually interacts with people who are there in a seamless way, in a smooth way. This is the robot we particularly consider. We had a couple of them. So we have a mobile manipulation capable robot with an omnidirectional drive, and then in addition with a small anthropomorphic robot on top of it that helped us to study how the robot should interact with people so that this interaction is as efficient as possible. The second part here is robots that learn and optimize knowledge and operations. So that's the KO part. And that's actually when we consider the environment. How does the robot fit into the environment, work efficiently with people, learn what they are doing, what they expect of it. So, and our most important, the overarching objective is safe and efficient intralogistic robots in agile production. So how can the robots, for example, make sure that they don't get into a situation where they need to hit the emergency brake? And efficiency we looked at different levels. So for example, in manipulation. One thing that we considered was, I hope the videos play, was picking and placing while in motion. So we initially had the idea that a forklift or a robot would actually not have to stop when it passes by a shelf and takes something from it. Here we implemented this with a robot close to an assembly belt. And then we looked in particular at one mode of efficient transportation, which is throwing. So the robot was supposed, what you can see here on the left, was supposed to be able to throw the last meter, so to speak. Now, where does this come from? Admittedly, first, we thought it would be real fun to do it. Second, robots can reach superhuman performance there. I talked to people who did that before, and they said, well, it works basically all the time if you know the geometry and the weight distribution of the objects. And then we talked to our industrial partners, Bosch, Siemens Household Devices, and we looked at their processes. And this is a hypothetical example, but they told me about it. So they actually have spreadsheets that shows these are the objects that we have, and this is here to the human workers how you can handle it. And we were really surprised to hear that they have one column which says
throwable? Can you throw this object or not? And these workers sometimes have a daily distance that they cover of 15 kilometers, and towards the end of the day, they are really happy that they can throw the last meters. So we generally aligned very closely to the real use case, also in terms of the parts and the structures. So you can see on the left side, you can see a picture from the actual process, and on the right side, how we actually replicated that in our demonstrations. We used the same shelves, we used the same objects. We had so many, they have 130,000 objects, more than 1,000 of them that you can throw, so we could actually gradually make the throwing harder for us. Okay, then we also collected industrially relevant data. So here I can just show this very briefly. This is a 3D model of the environment in which we worked, and this is a data collection for industrially relevant objects because YOLO out of the box couldn't really recognize them, at least not at the time. So we have a deep learning solution that actually fixes basically the object recognition part for us. Now, I said throwing, that really comes from the use case, and so we looked at it. And we looked at it in different ways. You start naturally, so I'm in the throwing part, you naturally start with a more or less standard configuration. So you have a standard robot arm and a 3-finger gripper. A difficulty here is that actually to have a gripper that opens fast enough was a bit of a problem. But then actually, if you know the object and if it's grasped in exactly the same way, you will always hit. But this was not the only thing that we considered. We also looked at the solution here, and that's what you will see is actually now a patent, an Italian patent, of throwing using infrastructure from the environment. So here we have this vacuum pump, and if you reverse the way that it actually, not sucks air, but actually blows, then you can also hit here the target. And then we started also in a parallel development, we started to build robot arms from scratch, which have more elastic elements. And here you see our robot 2024. That was the best we could do, 1.5 years ago, throwing a key with an elastic arm, and that's basically when we set up the project, Sami Haddadin and I, we were talking and we both played handball and we were wondering why the robot arms have so much power but can really throw not very far. And that is what we now see 2025, that we can throw further and also very precise. So this is what we investigated. And with these demonstrations, of course, we could go to fairs, and we did that, and I think that is part of the impact that we had, so that we could really show our results to people at fairs who could directly see what we can do. And here's another aspect. So this is if the box that you throw to is actually non-cooperative. So these children, we don't know exactly what they will do, how they will move the box, and the robot is supposed to still throw the ball into this box. And you see they are relatively well behaved, so the robot actually manages. This was during the Swiss Robotics Day in Lausanne at EPFL. And here you see a little bit more of a challenging child, and you see that sometimes the robot also has to be a bit lucky, so he is. But yeah, we were really lucky in this case. Okay, so very importantly also that here we actually reached 1,600 professional users and over 1,000 families and children to also be present at these, at these events. This was also important to us. Okay, then now a slightly different direction is if a robot now meets people, how is it supposed to behave? And so we first looked at the problem of the perception stack. So we developed a full stack for fast and real-time 3D object detection. I showed that already, human pose estimation and activity recognition, so that you actually have a view on a scene that looks a little bit like what I show in the background. And we did that for a pinhole camera and for a fisheye camera. And that was, I sometimes show a label here, so that was done primarily at the location of Bosch, but we were always working together here. So that is a result that went directly into a product, and this is the active shuttle from Bosch, who then was transferred to Bosch Rexroth. And here you see the robot is actually supposed to, or is used in order to transport these boxes. And when I yesterday checked the website, that was the picture on them. And I know Christopher Palitz from Bosch Rexroth is here. I don't know why they gave them this look now, but I will find out. And what you can see is, for example, our stack at work, where the person is recognized and can actually guide the robot with its gestures. Because you have seen that we have this full body model. So here is a result that directly was included. Another thing that we looked at is these robots are supposed to behave well and work efficiently in new environments. So we looked at ways in which they can learn how people move, their learning activity patterns. And we had, from a previous project, we had, for example, this map. After 6 days, robots could actually tell how people were usually moving there. That was a previous project, Iliad. And the problem is something that we discovered in an even earlier project, Spencer, where we actually looked at the process. Humans are showing their boarding pass at Schiphol Airport, and then the robot should actually bring them to the gate. It's very important that you know how people move there, otherwise it's super hard. So I think that EU projects are especially good for that. So developing new ideas that you then can bring to full blossoming in national projects, for example. So in this project, we looked at ways that you can actually learn motion patterns more in a time-related manner, that you can learn them continuously, that you can actually use analogies to computational fluid dynamics, and that you can use this model then to predict the human motion for up to 50 seconds. For that, we also collected data. Here you see, for example, human motion data, very precise, how they interact with industrial tasks, industrially inspired tasks in the vicinity of robots. And this actually is published and available as open source, or like open access data sets. Okay. We also, with this topic, we also have a long-standing workshop at ICRA, the long-term human motion prediction workshop, which ran through all the project and which will also have an additional edition in 26. So, final topic here is intent communication. So how can the robot show its status and how can it communicate what it's supposed to do? I just showed this one example. The robot indicates just by looking at the person that it is aware of it. Here we have a small robot. In Sweden, I worked with robots with 30 tons. When there's only narrow space, you want to be aware, you want to be sure that the robot has seen you and is aware of you. So here we actually then looked, in order to fully understand the interaction between people and robots, we looked at eye tracking. So where does a person look at when it's interacting with a robot? And we learned, for example, that if you have multimodal interactions, the gazes on the right side are much more centered. But this actually also brought the idea to and then we worked on a totally new way of understanding what humans do by semantic eye tracking. So you at every point we know what the person is actually looking at. But this brought us, sorry, this slide shouldn't be here, but it's nice to see. So we also had this at the Children's University. It's a very visual topic, and hopefully engaging the next generation of children. But what I really wanted to say here is that based on this eye tracking idea and understanding what the human wants to do, its intent, we actually fueled a startup company which is called Sapius. And so these are the founders. 3 of them were in Darko. What does it do? It's basically the idea that you put a mobile phone in front of you when you drive a car, and in the end, the car, so the mobile phone tells you what to do, and in the end, it tells you whether you have passed the exam or not. With this, We were on the Time magazine list of the best innovations 2025. We got the Popular Science Award, and we will actually receive the Edison Award in April in Florida. So what this does, and these are slides from the Department of Motor Vehicles in Virginia. For 120 years, the driving exam has been the same, but 2026 is basically changing through this startup company. We just recently sold this solution, so for the next 5 years in Virginia, people will do their driving exam with our solution, and we are currently negotiating with 27 by today of states who also want to purchase this. Finally, conclusion. So there has been a lot more. I'm already out of time, but it's very important for me to say. So there was lots of things that I didn't report on. I think that it's important that we did a lot of dissemination events, pages and pages in our reports. You might have wondered, I never had literature references. We had more than 120 publications. It would have been just too much work. We had a number of Best Paper Awards, 4 in the last period alone, and we were recognized in the Innovation Radar. Also, I think 6 was in the last periodic report. And finally, it was a great experience to work with this consortium. Also, great thanks for me. It was an excellent collaboration with our industrial partners. And I would also always see the PhD students, the doctoral candidates that we have developed who went on, that is already visible to strong careers, and also postdocs and other senior researchers who became positions because of this, or who were able to get good positions because of this project. Finally, we were talking about speed yesterday, so I would like to thank very much our project officer, Mariusz Baldiga, and also our reviewers, Markus Winze, Adam Schmidt, and Roland Cicalla, because they allowed us to interpret the work plan. So many things changed, and we were always able to, to kind of fit this into our work plan. Right, and then, of course, we want to continue this, and we are currently searching for funding opportunities. Finally, last 30 seconds I give to the people who work there to just say what they did. This is just a few of them. Thank you.
Motion prediction.
Maps of dynamics.
Human-robot interaction.
Elastic breeze throwing.
Risk-aware navigation.
Human-robot special interaction.
Contact source throwing.
Human perception and 3D scene understanding.
Object-level semantics.
Possession for manipulation.
Robotic manipulation.
Elastic manipulator for robotic throwing.
Thank you from Darko.
Congratulations again. Next one, DG Forest. We're going back to the green. Impressive.
Okay, thanks for inviting me, and it's my pleasure to talk a little bit about DigiForest. My name is Stefan Leutenegger from ETH Zurich. Come on. Okay, so at the start, when we wrote the proposal, the situation is that quite a substantial amount of the surface of Europe is actually covered in forests and woodland, 43%. And still, clear cuts are destructive, but actually the most economical situation, or the most economical way of doing forestry. At the same time, we realized that the data for decision making really lacks the kind of precision that we think would be necessary to improve the situation. So we set out with this idea of the project DigiForest, a 3.5 years project, starting in September 2022, with the goal of developing innovative robotics and analytics technology to enable sustainable forestry. The consortium started in this constitution. I was at TU Munich at that point and led the consortium. We also had partners from ETH, NTNU, Bonn, and Oxford on the academic side, and then WSL, which is a forestry lab also in Switzerland, and a few industrial partners, including our partner, the commercialization partner named Silver back then. And as you hear also in our consortium, there was a number of changes actually that happened. So Silver changed its name to Precision Forestry, PREFOR. I also went to ETH Zurich and then was replaced at TUM, and we had to also change the coordinator. So actually now I'm somewhat filling in for Cyril, who is the coordinator today. And we also added an additional partner, the University of Bolzano with Marco down here, and in a way an additional country. We had these 4 ambitions that we formulated. Robots, of course, on the one hand, teams of heterogeneous mobile robots that we wanted to use, that can create high-resolution data at really per tree level. So this element of precise mapping, creating precise data was very important as a actually basis for the next ambition, as a basis for decision-making to then support foresters. And finally, we also wanted to do autonomous or automatic harvesting with respective machines. So let me go through that a little bit. Starting with the robots. We have a forest here. We have these sort of larger drones that we can fly over the forest canopy and map from above, also with precise LiDARs on board. And then we have a bunch of smaller drones that we can also fly underneath the canopy inside the forest. That's harder. GNSS is not really available. So we'll have to address also those challenges related to that. We also have different kinds of drones. I'll talk a little bit about it, somewhat more lightweight, smaller ones, and a bit larger ones as well. And we have these kind of handheld devices to walk through the forest, as well as walking robots like these 4-legged animals. And then finally, we have the harvesters as well, right, that we can actually use to cut trees. So starting with the kind of mapping and SLAM type of work at the University of Oxford, they have developed this Frontier device that can be used for SLAM and map creation. It doesn't rely on GNSS, but also can record it, has a bunch of other sensors. There's also actually efforts in progress to commercialize some of this by itself. And so this can be used as a handheld device, as a backpack, but basically the same device can also be installed on a walking robot. So here you see some of their final work on really having a legged robot autonomously navigating through the forest, following this sort of lawnmower pattern, and at the same time doing SLAM, doing also loop closures. You can see the kind of red bars here that are the loop closures that have been identified while executing such a pattern, with the goal of having really accurate maps that it can actually create. On the side of the drones, NTNU has been working especially on very safe navigation through potentially very dense forests, using LiDAR as a basis for this. And then here this is some work on a control barrier that would ensure safety of the drone not crashing into trees. Again, all of this is without any GNSS, without any external motion tracking. On the other hand, we from TU Munich back then, now ETH, we wanted to have a slightly alternative solution and not rely on LiDAR, so we developed these kind of drones that only use passive stereo actually, and then use that as a basis to do SLAM and to stitch together these little sub-maps to eventually also form a large map that could be used as decision-making basis as well, obviously with slightly less precision, but at potentially a much smaller cost point that we could go further with this. This actually also awarded us the IROS 2025, so last year, best paper in robotics, robotic agriculture and forestry. Okay, then looking a little bit more at mapping. Of course, all of these robots will need their own mapping while they are being deployed, but this is not the primary goal of the project. The primary goal was to create high resolution and aggregated maps that would then benefit the forestry. And now this is about bringing these things together, doing post-processing with the data that was recorded, with the prior maps that the robots generated, and stitch them together, for instance, also across different platforms. Here we have the combination of backpack data with animal data. That is then two missions essentially that have been stitched together in one consistent map. And perhaps even more difficult actually it is to put together data from underneath the canopy and above the canopy, because you have almost no overlap between the two. So the guys have developed some smart ways of aligning these and making sure that they are actually consistent, such that you can then have a complete view of the forest and you can really extract data that is useful, like the tree height or the canopy volume and things like that. Yet another perhaps difficult situation is also to align these maps across seasons and across quite long time spans. As you imagine, the forests will change and we want to keep track of that change, but we have to first align this data and then to try and keep track of these changes, how trees are growing, for instance, which trees might disappear, which might appear, and so on. So we've also developed some algorithms to do that. Then the next element is decision support. First element of decision support is even to just segment such maps into individual trees. So we can do this now across different kind of maps with different levels of density and accuracy. And we have also developed some work around doing this live as the robot is being deployed, that you can already see. This is again a walking robot where the individual trees are actually located, and to extract key features such as the DBH diameter at breast height. This is really the sort of a key number for foresters, and we showed that we can achieve something like 2 centimeters of accuracy, which is in a way is what you need, right? It's the same as the human level accuracy that you get from today's measurements, where you just go around and actually measure these circumferences and diameters. And the output here really now is a spreadsheet, right? So even live, as the robot is deployed, in the end you get a spreadsheet that tells you where these trees are with coordinates and with the diameters. And it's actually then this data that is further processed by our partner WSL to feed things like forest simulators, growth models. So these types of inputs are going in, and they can run these models and derive further elements along the lines of biodiversity, relations to forest management, as well as climate change. Finally, I want to briefly talk about the harvesting element of it. So this is mostly work between the implementation partner, Precision Forestry, Pre4, and ETH Zurich, where they have retrofitted this quite lightweight harvester robot to minimize somewhat the soil compaction, so going for a somewhat lightweight, smaller one. And here you can see it in action. So first of all, it has to also safely navigate around using its own navigation SLAM stack, can avoid people on the road and go through the forest and off-road. You can also see the kind of LiDAR map that it's producing and the navigation strategies. So now it's going through the forest and it's going to find a specific tree that is supposed to chop, and here it is. So now it's identified it, and it can actually approach it and cut it. Okay. Right. And now it's cut. Okay. So the final few minutes I want to spend on actually the implementation partner's business and business intentions with the generated IP from the project. So as I've already summarized, we have the kind of UAV as well as under canopy type maps that we can create. These also include semantic segmentation. So they have access to this sort of IP and want to now monetize it in different ways. An obvious one that they are pursuing is for accurate forest inventory. That really the realization is that today we have relatively low accuracy in these methods to do really quite manual forest inventory, and that the value of the inventory data increases a lot with the type of precision that we can achieve now with our mapping solution. So this is even just the mapping element of all of it. They also want to, however, go towards autonomous operations. So perhaps there might also be licensing options that they're looking into, where the idea is that actually using some form of autonomy, autonomous harvesting, can save a lot of operational and capital expenditures. Perhaps on the sort of mission planning, digitalization side of things, there is an increase, but then actually you get a lot of the benefits once you are starting to automate some of these operations, especially actually they identified also the forwarding here as some somewhat substantial cost savings that allow you to totally go from to reduce the kind of cost base per cubic meter quite substantially, around 30 to 40%. There's also a realization that probably in a first wave of autonomy that we might see in this space, it will be more of an operator model of a service provider rather than companies buying their own fully autonomous machines, perhaps similar to the kind of ride-hailing services in autonomous driving, that this is more based on operators providing these sorts of services. So this will be the target for them. All right, with that, I'm also out of time. Thank you very much. Thanks, of course, a lot to all the partners and all the researchers that did all of this. Thank you.
And last but not least, Somiro. And thanks to the camera holder, I hope we have a final photo with all the winners at the end.
Maybe yes, but it's not necessary. Is this yours? Okay. I will just use it.
Okay, so welcome everyone. The last presentation is about the Somiro project, Soft Milli Robot. And I want actually to emphasize two things that Achim said before. One, if like a project needs to be successful, yes, you need to put in more resources. I think that also like in this project was really key to get things really done. And the second one is that such projects can help you with your career. And I'm such a person who this project helped in my career because like I am not the coordinator of the project. I was postdoc at EPFL before. My name is Florian Hartmann. And now, also through this project, partially, I'm a research group leader at the Max Planck Institute for Intelligent Systems in Stuttgart. To give you a bit of an overview of the project, we had like 9 partners, 3 million of funding for like 3.5 years, starting in 2021. And the project coordinator is from Uppsala University, Klaas Hjort. If you want to have his contact details, you can find them over there. EPFL, Max Planck Institute for Intelligent Systems, Johannes Kepler University in Austria, IMDEA Networks in Spain, Micronic is electronics and microfabrication company in Sweden. Riso Prestigio was Italian rice farming, high technologically advanced rice farming company in Italy. The Circle, an end user for aquaponics also like in the vicinity of Rome. And Warrant Hub was a management company in this project. So what is Somiro about? Like if you think of making a robot that explores like aquatic ecosystems, like a rice field or like a lake. We often think of like, yes, like water is an easy ecosystem to operate in. Like there's like usually vast spaces of water where we can operate in. If you think of the sea, right, there's like kilometers, nothing. But if we think of actually bodies of water that are more like the lakeshore or the rice field, smaller bodies of water, then things look actually quite different. And it is like more challenging to have like a really huge robot like roaming around. Like for example, if we look here, like a typical rice field, like rice plants are spaced 20 centimeters apart, which is like not easy if you build like a meter big machine, right? It was just like destroy the plants there. So the Sumiro project wants to develop like a miniature robot that can swim on water surface for the application of precision agriculture. For example, a robot that swims around in the rice field and can measure fertilizer concentration at various points in the rice field. The project itself started from a very low TRL level because mostly of the size of the robot. And the goal was to achieve like a new propulsion system that can work like in a miniature robot, achieve energy autonomy in this miniature robot, and also some sensing and communication tools that work at very low energy. And everything should come together like in this like biomimetic small-scale robot. So some of the key innovations that came out of this project are actually the propulsion unit. I will go a bit deeper into that with the next slides. But also like strategies to achieve like energy autonomy for super lightweight photovoltaic cells or solar cells. And also some very interesting sensing and communication tools that work with visible light, also together using solar cells to reduce like the complexity of like such a device. So how small is the robot that we developed? It's actually smaller than a credit card, around 4 centimeters by 4 centimeters. And that actually means you cannot buy anything, you cannot buy motors that you implement there, you really have to develop many of the hardware from scratch. So this is like the Sumiro robot that swims here like on the water surface, here through like the cluttered environment with these rubber duckies. And it's like swims on the water surface, is fairly small, 4.5 centimeters, 5.5, only like 6 millimeters thick. And we tested it here like in the simulated rice field where it's then was actually swimming through. In that case, actually remote controlled, not fully autonomous. What we used for actuation are soft electrohydraulic muscles that are high voltage actuators that make a bending movement. And with this bending movement, we drove like oscillations in a soft fin that you can see here. Like in slow motion, it's actually happening very fast. That works underwater, but also like on the water surface as well. And you only need 2 actuators to drive like this robot, and it can then swim forward if you use like both of those actuators, but it can also like turn if you use like one of those actuators. With that, we had to develop also fabrication processes along with it, that we can do this at different size scales or in different configurations. The smallest robots that we developed are actually 1 centimeter by 1 centimeter. They were also like swimming, like the integrated version was then slightly larger. As I said, we use high voltage actuators, so we also developed our own power supplies for it and integrated it here on a PCB for like a remote controlled operation. Here you can see that we can also like do a task with it, like pushing around objects in case like you need to clear the path of like the way. And here just a teaser on like how future autonomous operation can look like. If you really pack more sensing capabilities on there, then you can have also like a robot that finds like a light source and swims like to the light. Okay, so in this propulsion platform, what we did is we really developed like a monolithic platform that can propel on the water surface. We also developed like the electronics board for it, that it can actually swim in a remote controlled way, or like also like in a very simplistic autonomous way. All right, and then I want to also briefly speak about the solar cell technology that was mainly pushed forward by the Johannes Kepler University in Linz, where they developed a lightweight solar solar cell with like a record-breaking power per weight ratio. So usually if you have your solar cell on your roof, it has like a lot of like glass packaging, and if you reduce that and you manage to make a solar cell on an ultra-thin plastic film, then you get a lot of energy that you can harvest from the sun, but the overall weight is super light. And that is useful for many applications, and I have like 4 different areas where it made impact. So yes, you can put it on a robot, like here is an example of like a quadcopter drone that has here like an array of like a few solar cells where the drone can land, recharge, and then fly away. The technology is also promising because lightweight solar cells might be interesting for space applications when you want to send things into space. And this was also like one example where those types of solar cells were actually tested on a real space mission. You can not only power robots with it, but all kinds of wearable sensors. For example, imagine a face mask that has some biomedical sensors on it that you want to power with ambient light. You can use that using the same technology, or also like biosensors that you can wear on your skin. So those are like some areas where this solar cell technology made impact beyond the project. All right, so time is almost up. Where this project was successful is in many of like the subsystems actually that were developed within this project. We had like a miniature robot that we tested in a simulated rice field that was using novel artificial muscles and visible light communication to operate in a biomimetic vector. And some impact that is making beyond that, we are currently also developing like a new platform that is slightly larger and more integrated that can then be, that likely will be then published as an open source project in later this year or next year. All right, and with that, I want to thank you for attention. I want to thank like the consortium. I made very good friends over the years where I was like part of it. And yeah, my name is Florian Hartmann. My contact details are there. Also like the project coordinator, Klaas Hjort, you can find over there. Thank you very much for your attention.